research. The Large Hadron Collider is the most ambitious scientific experiment ever attempted. A 27-kilometer enclosed ring, punctuated by 4 enormous camera-like detectors, will mimic and record events seconds after the Big Bang, in the hope of finding the answers to life, the universe, and everything. ATLAS and CMS are the largest of these detectors. They are so huge that each has its own 2,000-person construction team. But before the scientists can begin to tinker with these mega toys, there's the small problem of creating a home for these enormous machines. That calls for world-class engineering.
Everybody was waiting for civil engineering to finish because the physicists can't do anything without the infrastructure in place.
John Osborne is the project engineer responsible for constructing the caverns to house these giant machines.
At this particular site, there was one small shaft going down to the tunnel, but that wasn't sufficient for LHC, so you had to excavate 2 massive new shafts and 2 huge caverns for the CMS detector, the site we're on now. This is the biggest cavern that's been excavated in this type of rock. On this one particular site, we excavated 220,000 metres cubed of rock and gravel to form these 2 new caverns, so it's a huge scale of construction.
These caverns are 2 of the biggest underground areas ever created. Physicists Dr. Bob Stanek from Argonne National Laboratories outside Chicago and Dr. Alan Barr from the UK's Oxford University are part of the team building ATLAS.
Behind me is one of the biggest experiments in the world. It's the ATLAS detector, and it's like an enormous, it's a camera really. It's a camera that takes pictures 40 million times a second.
At CMS, physicists Dr. Dave Barney and Dr. Austin Ball from the European Organisation for Nuclear Research are at the helm.
We're approaching the culmination in terms of construction of an effort that started 15 years ago, but it was started not for the sake of building something complicated, but for the sake of doing experiments in physics.
I've essentially spent my whole professional career working on CMS for the past 15 years. So I'm really excited by the prospect of actually getting this thing up and running and getting some physics out of it. And it really is just the start of the adventure. It's really just beginning now.
And the physics is earth-shattering. ATLAS and CMS won't be taking just any old pictures. They will be capturing the very birth of our universe. To achieve this, particles are accelerated along the collider's 27-kilometer ring so fast that they will reach close to the speed of light, covering over 16 billion kilometers in 10 hours. That's enough to get to Neptune and back. About 800 times every second, the particles will smash together right inside the center of CMS and ATLAS, mimicking the Big Bang. CMS and ATLAS are not identical, but they are built in parallel, so both can capture the results of these catastrophic collisions. It means the scientists can compare and check any results. They will snap away up to 40 million times per second, capturing data that scientists hope will provide answers to the elements of our universe that we still don't understand. This groundbreaking collaboration of hearts and minds has taken over 15 years to mature.
And
But underneath the skin of this collaboration, a battle is being closely fought. Alan Barr and his teammate, Bob Stanek, want the Atlas detector to be the first one to take the world-changing shots. To achieve this, they must have their detector built and ready first.
I think this is the first time in my lifetime that there's been a real chance to discover something completely different and completely new. And to me, that's very exciting.
When you look up in the sky, 90% of the stuff, or 70% depending on your favorite theory, is something out there that you don't know what it is. If we start to now make discoveries that help us understand what we don't understand, our life is going to be a lot more fun in the future, maybe a lot more easy in the future, maybe a lot more complicated in the future.
But the Atlas team is not alone in their ambitions. The CMS team is hot on their heels.
Bessie, we're meeting again with Jim tomorrow to try and...
Dave Barney and Austin Ball have worked on CMS for a decade and a half, and they don't want to be beaten to the post by Atlas. Both of these mega machines must operate for the experiment to succeed.
We don't know what we're going to find. We don't know the answer. So when we do think we've found something, having another experiment that's based on similar principles but done in a different way, if they also see the same thing, we can compare the two and have a really good idea that what we've found is real and it's not just a fluctuation, it's not something random.
The components for the collider are made in different parts of the world and put together when they arrive at the construction site. It calls for precise measurements.
It's been worked on by Europe, America, by Japan as well, by all sorts of different countries. So it's an enormous project.
We're looking for precisions of a millimetre or less on objects that are 14 metres across. And so this is pushing engineering to the limits of what can be achieved today.
Even the moon had to be considered in the calculations. Its phases have an effect on the mountains, causing the ground and the experiment to move. Tiny fractions, but enough to blow the entire project if they are not factored in. It's the biggest jigsaw puzzle ever attempted, and it's all happening in Switzerland at the European Organization for Nuclear Research. Better known as Cern, it's the largest scientific research project in the world. More than 7,000 scientists, half the world's particle physicists, use its facilities. Cern was established near the French-Swiss border outside Geneva in 1954 to study the building blocks of matter, the component of everything in the known universe. They haven't yet discovered all the answers, but in the process, Cern has given us the World Wide Web and highly advanced medical scanners.
Cern is a place in which people from all over the world, some of the brightest minds from all over the world, come together and sit and have coffee together and discuss the big problems of the day. You could be sitting there and someone say to you, well, actually, I've had this, completely new thought about dark matter, or a completely different thought about how the universe may have began. And you think to yourself, wow, that's a kind of a cool thing to find out over my coffee break.
The Large Hadron Collider isn't a new idea. For the past half-century, CERN scientists have smashed particles together. But this machine is bigger and better than anything that's been tried before. It's 7 times more powerful than its predecessor. It uses 120 megawatts of electricity every time it switches on, almost enough to power every household in the city of Geneva. The collider will help scientists answer key questions about our universe. What is dark matter? Antimatter? What are black holes?
We're looking for the most basic things that make up the universe, so the things that make up the atoms and the things that make up all material around us. One of the things that particularly interests me is that I hope that we'll be able to find out what dark matter is. Now, this is a bit of a freaky thing. We don't really understand what it is, and the words dark matter there just hide our ignorance, really. Astronomers have told us that there's something out in space which is pulling things towards us, but it's a freaky, mysterious kind of a substance because it's not made out of anything that we know. It's not made out of atoms. It's not made out of any of the forces that we understand. And it makes up much more of the universe than we do. So it's kind of like the dark side of the universe, and we've no idea at the moment what it's made out of.
While the scientists scratch their heads, the engineering teams crack on with creating the final resting place for the mega machines. Atlas and CMS are on opposite sides of the collider. They are too massive to be lowered into the cabins in one piece, so they are built in segments on the surface and then dropped down and bolted into place a section at a time. At the Atlas site, two shafts, 18 meters and 13 meters in diameter, drop down 67 meters to meet one of the largest caverns in existence, home for the gargantuan detector. Engineers forced their way through the sides of the mountain using powerful rock breakers.
For the caverns here, we just used excavators with hydraulic hammers. Very, very similar equipment that you would use on projects. For example, the last job I worked on was at the Jubilee line in London for the Metro. And the equipment there was very, very similar to what we used here, except here there's particles coming through the tunnel and not underground tubes.
Once the rock breakers were through, a thick green waterproofing membrane was installed and the walls of the cavern constructed out of reinforced concrete. The 10,000-ton concrete cavern ceiling, equivalent to the weight of over 2,000 rhino, was built and suspended in mid-air by 38 load-bearing cables until the remaining structure was built up around it. The concrete floor slab is 5 meters thick and strong enough to support the 7,000-ton Atlas detector without deforming. The sidewalls rose from the floor to the ceiling, replacing the suspension cables. The resting place for the mighty Atlas detector is so big it could hold the nave of Paris's Notre Dame Cathedral. Building the cavern for the CMS detector posed even more of a challenge.
There's two underground water tables on this site, if you like, underground rivers, and the water's travelling at quite a high velocity. So we knew we'd have to come up with a novel technique to excavate these shafts. So we decided with the contractors to use a technique called ground freezing.
Pipes were drilled all the way around the shafts. Salty water at minus 25 degrees centigrade was circulated inside these pipes.
And then eventually, after several weeks, the water in the ground that existed started to freeze around every individual pipe. Then after 6 months, we had a wall of ice that was 3 meters thick all the way around the shaft, going right the way down 60 meters to the rock.
The wall of ice protected the engineers from the underground water. It took 6.5 years to complete the 53-meter long, 27-meter wide and 24-meter high CMS cavern. The water pumped from the CMS site and the thousands of tons of excavated rock was put to good use.
The environmental aspects were top priority for Cern. Before we started this project, we did a big environmental impact study, and the landscaping and the disposal of the rock was one of the key issues, because there's more than 500,000 meters cubed of rock that we excavated from all the caverns. So on this particular site, we have about 200,000 meters cubed. This is all the excavated rock from CMS. So we've landscaped it all. We've planted trees and shrubs. We've created a footpath all the way around the site from the local village around this water basin. So this is where all the water from the underground that's captured behind the membrane is pumped out. It all comes to this lake before going off to the local rivers. So we put a lot of thought into the environmental impact of the project.
The CMS cavern was finished 20 months later than Atlas. The caverns are ready, so the detectors can be lowered into place. CMS has 15 big segments, and it takes months to connect each one before the next is lowered. But moving the detector in a single piece isn't an option.
It weighs about 12,500 tonnes in total, and there's really no crane in the world that can actually lower down 12,500 tonnes 100 metres. So we were kind of obliged to build it in sections of a manageable weight. So the largest piece, this one, is 2,000 tonnes, which is still an enormous load. But building it in slices also gives us a lot of flexibility. It allows us to open things up, allows us to do various things on, let's say, this part, while we're still working on the other parts that are still upstairs. So it gives us a lot of flexibility to play around as well.
A slice of CMS lowered a few months ago has been connected. It's time for the next segment to begin its descent. It's a landmark for Dave and Austin's machine, and it will bring them level with Atlas's schedule. The detector's 18-metre wide central piece weighs more than 5 jumbo jets and will manoeuvre into a hole with just 20 centimetres to spare. Austin makes sure the operation runs smoothly.
The gantry crane itself, it isn't like most conventional cranes. There's no drum on which the cables are wound. Instead of that, it's a bit like lowering an object attached to a rope by passing it hand over hand like this. So there are actually 4 sets of jacks which operate in this fashion, and they're synchronized together by some pretty sophisticated software. Our contractor is very experienced in this sort of thing. Their main recent experience is actually in putting roofs on large buildings in a single piece. So they're very used to lifting one-off, very heavy objects.
Each slice of the CMS detector can weigh up to 2,000 tons. So it's like lowering a herd of elephants. The floor of the building is reinforced to take the weight of this machinery as it sits ready for the descent.
Obviously, we had to come up with a clever solution to stop the detector falling down the shaft, so we came up with this idea of a sliding concrete lid, which really is a feat in itself. It's 2,000 tons of concrete. It slides on rails using hydraulic jacks. It's pushed from the open position to totally cover the top of this shaft.
4 cables will hold CMS as it descends. The cables are specially constructed to stop the tendency for the load to rotate or swing like a pendulum as it lowers. With only 20 centimetres breathing space, the slightest movement could be disastrous. Dave and Austin are suffering last-minute nerves.
This should arrive down in the cavern, 100 metres down, in about 7 or 8 hours from now. And then it will, over the next few days, be released from the cables. It will move a little bit in the hole underground. And then a really big work starts on this piece, which is to put all the cables, all the pipes that need to communicate with the detectors that are going to go inside of this. After that, the remainder of the experiment gets lowered down, so there are a few more bits in this hole on the surface to be lowered. There's 6 more really big pieces. They all go down smoothly as this. Some other pieces get added, central elements, central detectors. All gets pushed together. In effect, a big button says go, gets pressed, and the whole thing works. It's, of course, the principle of it, at least.
If the calculations are even slightly wrong, and the bottom of the shaft isn't big enough to let the load through, it will be lifted back to the surface, setting the project back by months. It's a nerve-wracking time for the 2,000 scientists from around the world who've been involved in designing and building this experiment. 3 hours into the operation, and just 5 meters into the shaft, there's an unexpected problem. Someone has pressed the evacuation alarm. Everyone has to get out. It's the last thing that CMS needs. The descent is stopped, the component hangs precariously, and the team wait for answers. At the Atlas site, Bob's also having a bad day. They already have most of their mighty machine underground, but putting it together is causing headaches.
At the very beginning, people said, yeah, we'll build this thing with all this high tech and we'll bring it down, we'll test it in the lab, we'll bring it down, we'll turn the switch, and it'll work. Well, one thing that we learned is that does not work. We test in the lab, bring it here at Cern, test it at the surface. It doesn't work. We fix it at the surface. We said, okay, it's certified, bring it down. We bring it down, test it. When we bring it down, it doesn't work. Okay. So we're constantly, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, we're testing and repairing. And stupid stuff that's breaking. It's the connectors. It's the screws that we forget about. It's the wires that aren't soldered well enough. The high-tech stuff seems to be fine, but it's the mundane things that you just take for granted that fail.
But Bob's teammate, Alan, puts a brave face on the matter.
This is the first time that anyone has ever tried to make something like this, and every day we find something that's never been explored before. We find problems with cooling, we find problems with trying to get material in, but that's part of the fun of the thing, is really trying to solve those problems. That's why we love this subject, that's why we try and do it.
The physicists are so demanding, they need this precision to not miss any energy going through gaps, that it has to happen. And at the end of the day, human beings being what they are, solve the problems.
While Bob battles with his technical hiccups, at CMS, the alarm was a false alert. Lowering continues. Dave and Austin need to connect this piece to catch up with Atlas. After 10 hours, the component is in position. It's a moment of triumph for Austin, Dave and the CMS team. And it means they are neck and neck with Atlas.
The tension's coming off the gantry cables behind us, which is the indication that we don't need the gantry anymore. This object is now resting on its air pads on the floor of this underground cavern.
I've been on CMS for 14 years now, since quite early days when things like this were just drawings on a few bits of paper. To see this in real life, you know, it's the culmination of an effort by a huge amount of people, and to see it happen now is absolutely amazing.
Really, this is the beginning of the last lap for CMS in being ready for the beams colliding. So I'm expecting that the team will want to party tonight, and I think they've really earned it.
It's great news for the CMS team. But are they celebrating too soon?
My prediction is that they're going to be in for just the biggest surprise as we were. When they turn on, their stuff is not going to work. And they'll be at that point probably for the next year.
Look at us! Yay!
I can see that we're neck and neck as far as the race goes, and I can see that in the future things are going to really heat up whenever we get to the time for the first collisions.
2 days after the party, and the CMS team is well aware that their detector is far from complete. More enormous parts must be lowered for assembly on the floor of the cabin, including the massive 300-ton calorimeter, which measures energies of particles. then barrel rings, each weighing in at 1,500 tons, followed by these huge discs to plug it all up, making it into a massive cylinder. Dave knows that's just the starting point.
A lot of pipe work needs to be done, a lot of cabling for all the detectors that are going to go inside the solenoid that really do the measurement of the energies and the trajectories of the particles that come out of the collisions that we're going to see.
Scientists design these mega detectors, but every available building and construction skill is needed to make them work.
Lots of the jobs that are being done are actually done by trained electricians, trained plumbers, trained builders and engineers, welders as well, as you can hear in the background. But putting all of this together with sub-millimetre precision takes it to a whole new level, really.
Even with the monumental task ahead, Dave stays optimistic.
There's still a lot of work to do, but we're on course. It's all going very well.
Over on Atlas, Bob refuses to be swayed by this optimism as his bad week continues.
Nothing works. Every day it's something different. So on Monday, you have a photo tube that doesn't work. Okay. Tuesday, you go and fix that photo tube. Wednesday, you go do something else, your power supply doesn't work. And it's a continuous thing. It's, if it's not electronics, it's cables or connectors or computer programs or things like that. That's pretty much the most frustrating thing at the moment. Hopefully, it's settling down, but we don't see the light at the end of the tunnel quite yet.
Building the detectors is tough, but it's only part of the challenge. The detectors need something to detect, and that means collisions. The collider itself must be ready to take on the speeding particles. It's the most exciting part of the project for Alan and Bob.
I mean, I think it's amazing to think that right in the middle of that, two beams are going to hit each other, each with the energy of an express train, right in that really fine point there, and they're going to blast out through all our sensitive equipment. So it's an incredibly violent thing that's going on in the middle of this, and yet we're trying to measure it so precisely, to much more precise than the width of a human hair.
We're now right at the center of collision. So the protons, if I look that way, protons are coming at me. If I look that way, protons are coming at me. Right in the center here is where they'll collide. So all this equipment where I'm kneeling is to measure the high density of particles that are going to come out.
Particles are tiny components of atoms. There are many different types of particles. One is the hadron, as immortalized in the name of the collider. The particles are steered round the collider tube by magnets. There are over 1,200 magnets curving the particle beam, 400 focusing magnets, and 5,000 to correct the beams if they stray off path. Fitting onto the magnets are over 12 million steel collars. Even with this amount of pulling power, the collider needs more to create a big enough magnetic field to move the beams. The magnets need to conduct a current of 10,000 amps without resistance. This means they must be very, very cold. Huge refrigerators filled with liquid helium keep the collider at minus 270 degrees Celsius. It's the coldest environment in existence, colder than even deep space. Over 10,000 tons of liquid nitrogen and 60 tons of liquid helium is needed to cool the system down. A highly sophisticated cryogenic system produces and maintains these unprecedented temperatures. It's the world's largest fridge, and it's big enough to hold 150,000 sausages. The new technologies and uber precision involved in building this machine demand some pretty intense testing.
It's just incredible how much testing has gone on. We want to be 100% sure that whenever we put our piece of the camera down underground, that as much of it as possible worked on day one. And so it was testing and testing and testing.
But sometimes, even the most stringent testing can still leave problems in the works. As Bob knows, his week goes from bad to worse. He has just been alerted to a technical problem that could seriously delay the Atlas project. And fixing it isn't easy.
We found a problem in our electronics. Some stupid things. Basically, we're replacing all these little tiny connectors because we find that they're not reliable. And this is causing big headaches for our system. So these guys have pulled out our front-end electronics. And so to repair these things, you have to undo the cabling at the end, yank this thing out, and then make the repairs, and again, in cramped quarters, putting on little dinky connectors like so. And it's just not a fun job to work in this environment. 3 stories of scaffolding just to get to this position where you have to work even harder. And then you forget your screwdriver, which is even worse.
Bob, Alan and the Atlas team are going to need a change of luck if they're to close their doors before CMS.
Put it back and
They have a chance to make up some time. Schedules have changed and they have been given a slot to lower a crucial piece of Atlas sooner than planned. This enormous 240-ton part is an end cap. It's one of the world's biggest magnets. The magnet is 11 meters in diameter and weighs 240 tons. It's a major hurdle and a key component. There are only small clearances at the bottom of the shaft, and the crane operators need to make sure this piece doesn't touch any of the other components. Easier said than done. It's a chain of events that need to run like clockwork. Down in the cavern, Bob looks forward to the next part of the detector slotting into place.
it will come down this shaft and be lowered on this structure here. It'll be connected to the cryogenics, and then eventually it'll be put into place, snuggle up inside those grooves. That's going to be a wonder to see. This place will be closed because if something happened, it would be like a bomb going off if the thing was to drop.
Suddenly, Bob gets called to the surface. Something is very wrong. The magnet is too big to fit inside the building. While Bob and Alan face their worst nightmares, over at the CMS detector site, they have challenges of their own.
All of these particle detectors that are going to detect the traces of the particles produced when the protons collide, all of them are sensitive to temperature, so their characteristics will change if the temperature changes. So we have to cool this object and keep it at a very specific temperature. And in fact, parts of the detector have to be at a temperature stable to a 20th of a degree, which is quite a challenge with an object of this size and complexity.
Not everything on CMS can be seen. There are teams working in every available crevice.
Actually, there's something like 200 kilometers of cabling installed between the experiment and its electronics racks next door. And you can see here a large number of pipes for gas and cooling, something of the order of 30, 40 kilometers of pipe work been installed as well. And as you can see, it's not finished yet. But we expect that by the end of this year we'll be in good shape and everything here will be finished, and that means we'll be able to operate the whole system.
Centimeter clearance between those.
Over at Atlas, Bob finally sees his component move inside.
There was some back and forth about what exactly to do. And it's reminded me of the old story about the little boy and the truck stuck underneath the viaduct. And all the guys are standing up there looking at what we do to the top. And the little boy said, why don't you let the air out of the tires? And, gee, that's smart. Well, anyway, the physicists suggested that they take those middle beams out. And that would have been a possibility. But no. The engineers decided they had a different idea. So what they did is they got a big old heavy-duty crane. They got a acetylene torch with an extra long hose. And they brought the guy up to the top, and he burned out a hole of the building. So you can see where that chunk was taken out. They needed 20 centimeters to get that detector in. And so they cut out that chunk from the top over there with an acetylene torch, and they drove it in. Okay. It worked, because I saw them working on this at about 1 o'clock in the afternoon, just before we started. And then here it is now 4 o'clock, and they're finished.
The extra work has put Atlas back by a day, but they are still ahead in the build schedule. The next morning, Bob is more optimistic about the job ahead.
Once it gets to the other side, the top of the barrel toroid is too high for our crane to reach. So what has to happen then, it's going to be driven with the cylinders extended way up till you get to the next shaft, and then it has to be lowered down by about 5 meters into the hole. 5 meters ought to be enough then for our crane to lift it up on whatever fixturing they need, and then it'll be dropped down the A-side shaft to its resting position. Once it goes in, I can complain again because I lose all my access and I can't fix my broken stuff. And then I have to wait maybe till next year, and on the story continues. But what are you going to do?
The Atlas magnet begins its slow descent. These crane operators lift submarines from the bottom of the ocean, but this is a whole new challenge. While the Atlas team lowers their enormous cargo, John Osborne has discovered a problem deep underground in the cavern itself. Moisture is causing the rock face to move.
You're excavating a massive hole in a rock that's existed for billions of years, and the rock wants to continue moving when you take out this void. So we've got to try and resist those forces by concrete.
These caverns are built around existing tunnels, so any weaknesses have to be repaired.
This is the concrete lining for the cavern. Now on this side we have the rock mass with an old shotcrete lining, which is just sprayed concrete that was done 30 years ago. So what's been happening over the past few years is the rock's been moving and swelling through moisture, and it's exerting pressures on the concrete, which is causing cracks to open up in the concrete lining. So now we're having to drill through the concrete right into the rock, 6 meters deep into the rock, insert new anchors, new rock bolts with a head plate fully grouted, and that withstands the pressures of the rock, holds the rock in position, and stops any more unwanted efforts being put on the concrete wall.
Back at the Atlas site, after a tense descent, the huge component lands safely.
These big magnets for the end of the machine were just on the limit of what the cranes could take. So the cranes were designed just to be able to take those. Of course, they're over-engineered a little bit, but whenever you see something that's 280 tons going down on cranes that say they carry 280 tons, then you get a little bit nervous. But also at that point, our bits of apparatus were already underneath it. So if anything had dropped, not only would it have destroyed those bits, but it would have destroyed absolutely everything. And so the engineering that's gone into getting all of those enormous bits of stuff right is impressive. And of course, everyone was biting their fingers as these things went down. It was a nerve-wracking job.
Alan and Bob can at last relax. The most difficult stage of their construction is over. Atlas has lowered all its parts ahead of CMS.
Our detector is complete. It's underground, it's sitting there, and we're actually taking pictures with it.
These early pictures are not of colliding particles, Atlas is snapping away at another mysterious cosmic phenomenon.
We're taking pictures of particles coming in, zapping in from outer space. So not many people realize that as they sit there having their cup of tea in the morning, that they're being bombarded all the time. They're being shot. They're little bullets, little particles that are produced out in the cosmos, out in the galaxy. In fact, we don't even really know where. And they zap through, they smash into the atmosphere, and they're hitting us all the time. So they're about 1 per second of these cosmic ray particles that are zapping through our bodies. I suppose that surprises people. It's not something that everyone knows, but it's been going on for the last 4 billion years. It's not going to stop anytime soon. What those particles can do for us is that we can use them basically as tests. Nature has provided these enormously high energy particles that fires itself through our bits of kit, and we can use them to prove that our kit's working. And that's really rather convenient for us.
But it won't be too long before the collider is switched on and the real science begins.
All the parts are down there, all of the magnets are in the tunnel, the magnets are being cooled down. Step by step, we're approaching that critical point where the big red button's going to be pushed and things start hitting each other.
The sheer quantity of information captured by these detectors will create a new problem for the world's greatest minds. They have to find a way to store, analyze, and then understand it.
There's about 200 CDs worth of information that's being produced in every second from all of these collisions. And what we've got to do with that is play the game Hunt the Particle. We're trying to find those particular events, which are the ones which are interesting to us.
Farms of computers will count and trace the multitude of particles produced by the collisions, generating 15 million gigabytes of data annually. This data is sent around the world for 5,000 scientists to analyze in 500 universities. So the next generation of the World Wide Web is being devised. It's called the Grid, and it's a global network of computers and software designed to process the data recorded by the collider and its detectors. It has taken both CMS and Atlas over 15 years to get to this place. And Atlas has finally won the race to be the first in position. Bob can forget about soldering irons, connectors, and lost screwdrivers, and focus on the science.
So at this point, it's sort of a bittersweet time, because we spent 10 years touching all this equipment, fondling our little pieces of iron, knowing every piece of intricacy and nuance of this detector, and working with hundreds of people over the past 10 years from all over the world. We've drank vodka, coffee, beer, and who knows what else. And interactions with those people are going to stop. On the other hand, it's the time now when we expect to have collisions and we start to do some physics. So that's why I say it's sort of bittersweet, because all the fun stuff that we've done in the past is over, and now comes a new area for adventure.
The Large Hadron Collider and its giant detectors have broken every engineering and scientific barrier and had an enormous impact on the lives of the people involved. But with the job well done, it's time to move on.
To some extent, my responsibility will change now, because we essentially we will have delivered a piece of apparatus, but we all change roles at that point, and I will actually be quite interested to revert to a role that I've enjoyed in the past, which is actually trying to understand the particular idiosyncrasies of a one-off, customized piece of equipment of this sort of complexity, which I think a lot of people find challenging, and I certainly do as well.
For the LHC, the big results of it will come out whenever we turn that machine on. And that's going to be the exciting time for that. It's up until now, it's been really 10 years worth of preparation and the excitement of the future.
Having taken a decade and a half to build, at a cost of over 3 billion euros, the Large Hadron Collider and its giant detectors will only have around 10 years to find the answers to life, the universe, and everything. After this, the world's biggest atom smasher will reach the end of its useful life, and a new collider will take over.